In today's video, we're going to go over some methods of doing substitutions on aromatic rings. And so we'll begin with SNAR, which is a nucleophilic aromatic substitution, and it proceeds through an addition-elimination mechanism. And so the first thing that's going to happen is some electrons on the OH are going to attack a carbon with the chlorine or with the leaving group on it, and this double bond is going to kick over to be a lone pair on a carbon. That's going to give you a structure that looks like this. And as you might have guessed based on the bracket that I started with, and I didn't draw it big enough, this complex has resonance. And so these electrons can kick over and down like that. This time I'm going to draw out my NO2 group. Because that NO2 group can help stabilize this resonance structure by accepting those electrons and kicking some more electrons down on oxygen. Oop, that's not a double bond anymore. And we can move that pair of electrons one more time around the ring. So I'm going to kick these back up in this direction. Like this. This intermediate is called a Mesenheimer complex. And SNAR works on electron deficient aromatic rings because of this resonance structure here. Without this resonance structure where the nitro group is helping to stabilize the electrons in the aromatic ring, this reaction doesn't work. And then in a final step, we do an elimination. And so this pair of electrons can go back to carbon and chlorine will leave. You wind up with this substituted aromatic ring in which we have replaced the chloride with an OH to create a phenol. SNAR reactions work on a variety of substrates with a variety of nucleophiles. In this example, we have a dinitro benzene with a halide. X is representing a variety of halides. And this reaction works as the last one to substitute the halide for, in this case, a methoxy group. Our nucleophile in this case was a methoxide, and so we're substituting the halide for a methoxy group. And this works for a variety of alkyl halides. And unlike SN1 and SN2 reactions, the fluorine is actually the fastest to eliminate. So fluorine reacts at a rate of arbitrary units 3,300, and it actually reacts much faster than chlorine and bromine, which both react with a relative rate of about 4.3, which are slightly faster than iodine, which reacts with a relative rate of about 1. And so the fluoride is actually the easiest alkyl halide to eliminate, but all of them can undergo SNAR type reactions. SNAR reacts with a variety of substrates. There's 2 requirements, however. The first one is that the electron withdrawing groups must be ortho and para to the leaving group. If the electron withdrawing group is in the meta position, you don't get that extra stabilization that we saw in the Mesenheimer complex on the previous slide. And the other requirement is the incoming nucleophile must be a stronger base than the leaving group. So this means things like N minuses, so sodium amide is also a good nucleophile. In this reaction, we've seen O minus, like OH minus and methoxide. Those are good nucleophiles in this reaction as well. There is a second type of nucleophilic aromatic substitution that is known as the benzyne reaction. This reaction proceeds through an elimination-addition reaction. So SNAR was the opposite order. It added and then eliminated. In benzyne reactions, we see elimination-addition. The first thing I want to do is look at a couple of examples of this kind of reaction. Notice the extreme conditions here. So we're at 340 degrees Celsius to get this reaction to go. But this reaction proceeds smoothly and gives a single product where I've replaced Cl with O. And if I look at the next one, slightly less harsh conditions in terms of temperature, but amides are stronger bases than OH, and so it's a better nucleophile. And this reaction, again, proceeds cleanly to replace Br with NH2. At this point, it is unclear why we have to invoke a different mechanism in this reaction than we did in the SNAR mechanism. But when we look at substituted benzenes, it becomes more complicated. In this example, we have 4-chlorotoluene. And this reaction proceeds cleanly, but it gives a mixture of products. The first product is the one you expect, where the chloride has just been replaced with the OH. The second one is unexpected, in which the OH is added to the position next to where the chloride was. And in this case, we get a meta substitution rather than a para substitution. And in order to explain that, we have to look at a different mechanism. And the mechanism of benzyne goes through an elimination-addition mechanism. And so the first thing that we're going to do is do an elimination. And in order to do an elimination, I first have to sprout a hydrogen. And this base is going to do base things and pull that proton off, which is going to give some electrons to that carbon to form a new bond and kick this chlorine off. That's going to result in a very unconventional intermediate known as benzyne. Benzyne is a benzene ring in which one of the double bonds has now become a triple bond. This should ring alarm bells everywhere. This is a highly unstable intermediate. Having a triple bond in the middle of a six-membered ring is very, very difficult. And so this is going to react with just about anything. In this case, we just formed water. And so water can attack this carbon, like so. And you generate this weird intermediate that has both a positive and a negative charge in it. That negative charge is quickly going to pick up a proton from this protonated phenol to generate your substituted benzene and the 4 substitution. If we go back to the benzyne intermediate, there's no reason that water can't attack the other carbon to produce this intermediate. Which again is quickly going to grab a proton off of that protonated water to give the meta-substituted product here. And you get these in about a 50-50 ratio, assuming that sterics does not play a huge factor. And so this new mechanism explains how you can get both the isomers of the 4 substitution and the 3 substitution. In the last slide, I said that benzyne should ring alarm bells because it's so unstable. You have a triple bond in the middle of a 6-membered ring. Why should that ring alarm bells? Well, if you think back to how pi bonds are formed, in the 6-membered ring of benzene, you have a pi cloud that is formed by a whole bunch of p orbitals on each of these carbons. So this is the orbitals, and these orbitals are overlapping to form a bond between that carbon or the two carbons. But remember that two p orbitals on the same carbon must be orthogonal to one another. So if one set of p orbitals looks like this, the other set of p orbitals has to be perpendicular to that or oriented on this ring like this. There are two problems with this. Number one is if this are actually p orbitals, then this must be an sp hybridized carbon. And if it's an sp hybridized carbon, it should have 180-degree bond angles. It doesn't. It can't have much bigger than 120-degree bond angles because of the geometric constraints of a hexagon. And so what actually takes place is it doesn't quite fully hybridize, and you wind up with not quite full p orbitals, but some hybrid that includes a little s character, and so one lobe is a little smaller than the other. And you're trying to form a bond with orbitals that aren't really even pointing towards each other or aligned. This has poor overlap. And so this bond is very weak and will readily react with many, many things. We've seen one way to generate benzyne in which we do a traditional sort of elimination and deprotonate the carbon next to a leaving group, which then kicks some electrons over to form a double bond and kicks off that leaving group. But there are a couple of other interesting ways to generate benzyne that can be useful in certain reactions. And so here I've treated this weird carboxylic acid with diazonium salt substituted. They're ortho substituted with sodium hydride. And so in that first step, I've got H minus, which is going to deprotonate the carboxylic acid to generate a carboxylate. Plus hydrogen gas, which escapes the reaction. If you heat this up, this will automatically decompose. Those electrons will kick over, which kicks these electrons over, which allows your diazonium salt to leave, and you form benzyne plus N2 gas plus CO2 gas, which all escape the reaction and leave you with a very reactive benzyne that you can then add a new reagent to. Another method of generating benzyne is to treat a ortho-dibromobenzene with magnesium. So in the first step of this reaction, magnesium inserts itself in between one of the bromines and the benzene ring. And remember that we can really treat a Grignard reagent or a organomagnesium as if it reacts as a carbon minus and then this MgBr plus is floating around. And that carbon minus with a leaving group right next to it can eliminate to kick those electrons over And that Br out, which again is generating benzyne without a whole lot of other reactive substrates around. And so now you can add another external nucleophile to benzyne and do other chemistry. One of the more interesting ways to use these alternative methods into benzyne is in a Diels-Alder reaction. So in the last slide, we saw that mixing this compound with sodium hydride would generate benzyne. Like so. And benzyne is an excellent dienophile. Reacts in a Diels-Alder reaction. And so these electrons are going to attack the diene, which is going to kick these electrons down and kick those electrons across and give benzene with a new 6-member ring and a double bond across. Similarly, we saw that this ortho-dibromobenzene with magnesium will generate benzyne. Which can react with furan, also in a Diels-Alder type reaction, where these electrons come in and attack here. This kicks down, and these electrons kick over. To generate this fused ring system. Like so. So benzyne is an excellent dienophile and will react with a wide variety of dienes to form these fused ring systems where one ring is an aromatic ring and the other is a cyclohexene.